Welcome back to the deep dive. So if your work touches on, the cutting edge of scalable machine learning, you are probably constantly managing this foundational tension in sequence modeling. You've got the sheer, context-aware power of the transformer architecture on one hand,
Right.
and then the revolutionary efficiency offered by state space models, SSMs, things like Mamba.
Exactly. We all know those trade-offs. Massive compute for transformers, linear scaling for SSMs.
But what if that efficiency, what if it comes with an inherent, an unbreakable mathematical limit?
Yeah, that's really the core question here for this deep dive, isn't it? We're digging to the paper to infinity and beyond. Tool use unlocks length generalization in state space models.
Right.
And this paper, it doesn't just, talk about this tension. It actually gives formal proofs and some pretty striking empirical evidence. It really forces us to rethink the whole competitive landscape between these models.
Okay, so our mission today is pretty clear. We want to give you, the expert listener, a professional, comprehensive, and strictly non-speculative analysis of this paper. We're going to unpack the rigorous definitions they use, like long-form generation. We'll examine those theoretical negative proofs that seem to hold back GSSMs.
Right, the limitations.
And then look at the, frankly, surprising positive result that seems to pop up when you add interactive external tools. And they validate this across arithmetic, algorithmic reasoning, and even realistic code-fixing tasks.
Yeah, and the central argument, the thing we should probably keep in mind throughout this discussion, is that these generalized state space models, these efficient bounded memory architectures, they do have this inherent theoretical limitation, at least when it comes to what the paper calls truly long-form generation.
And this is the kicker.
But this hard constraint just completely vanishes when they're augmented, specifically, and this is key, with interactive external tools.
Okay, so that initial takeaway really changes the game then. Tool-augmented SSMs can actually achieve what they call length generalization on problems that are, computationally tractable.
Right, yeah.
Which suddenly makes them look like a potentially superior and definitely far more efficient alternative to those quadratic transformers, especially in these sort of dynamic agentic settings where you need iterative reasoning and potentially unbounded contexts.
Exactly. So let's maybe start by grounding ourselves in the known limits of the current, gold standard.
Yeah.
The transformer.
Yeah, the inefficiency of the transformer is almost like machine learning folklore now. But it's worth being precise about where the bottleneck actually is. We're talking about the attention mechanism, right?
Right. The limitation is really just pure mathematics applied to compute resources. The computational complexity, it scales quadratically with the sequence length dollar.
Right.
Yeah. And that comes directly from having to compute those pairwise attention scores. Every token attending to every other token in the sequence. Specifically, it's that matrix multiplication, the QTK part, that generates that big world times old dollar attention matrix. That's the culprit.
And yeah, while we have optimizations like key caching, which help with memory,
storing keys and values,
and things like flash attention can dramatically speed up the time it takes by optimizing I/O.
Yeah. Makes a big difference.
The fundamental asymptotic dependency, that LL$ compute cost based on length, that structural limit is still there.
Correct. Memory use, thanks to those advances, often gets close to linear, maybe order UKO. But it's the compute cost that's the real hard cap. It prevents truly efficient, arbitrarily long context processing.
And the structural problems only become more critical recently, hasn't it, with the rise of these complex reasoning paradigms? We're not just asking LLMs to, summarize text anymore. We're asking them to do long-form, iterative reasoning, things like chain of thought, which really took off a couple of years back.
Exactly. Generating a CoT sequence that might stretch over thousands of tokens to solve some complex problem. Well, being able to handle that length efficiently becomes absolutely crucial.
Yeah, indispensable.
And that necessity, that's what really drove the creation of alternatives. Models like linear transformers, H3, RetNet, and especially these SSM variants like Mamba, they were all engineered specifically trying to get computational and memory scaling down to linear in dollars.
The paper actually introduces a useful formal category here, generalized state space models, or GSSMs, and it's quite an expansive definition.
It is, yeah. A GSSM, formally, is basically any model where both the memory footprint and the per-token compute time are fixed, regardless of the sequence length.
Okay.
Think of it like having a fixed-size internal working memory. And this definition, it captures the classic RNNs like LSTMs and GRUs, but also the modern, really high-throughput architectures like Mamba.
Got it.
And, importantly, it also includes some clever transformer variants, those that use a fixed-size local or sliding window attention.
Ah, because their total context memory is bounded even if the input sequence gets super long.
Exactly. So the standard globally attending transformer, it's explicitly not a GSSM by this definition.
Because it's KV cache, its main internal memory for context has to grow linearly with the sequence length $.
Right. So the GSSM is the efficient one.
Mm-hmm.
But here's where that theoretical negative result kicks in. The paper formally proves that the bounded memory of a GSSM basically guarantees failure on these truly long-form generation problems.
Wow, guarantees failure.
Yeah, this is the critical theoretical pitfall we need to get our heads around. It stems directly from the very design choice that gives GSSMs their efficiency, that fixed internal state.
Yeah.
If the task needs you to store or refer back to more information than that fixed state can actually encode, well, the model just can't succeed.
Okay, let's dive into the theoretical framework itself then, because they define the problem really rigorously before they prove the limitation. We need to sort of dissect their formal definition of a long-form generation task.
Right. This is definition 2.2 in the paper, and it's really a cornerstone of their whole argument and centers on this complexity parameter, null,
Okay.
which defines the size of the input and output spaces, 700 miles 1.
Yeah.
Now, a task 5-hour paired with some data distribution, let's call it the dollar, is defined as long form if as dollar gets bigger.
As the problem gets harder.
The minimum support size of mass alpha, which they write as Samana mouse dollar, is monotonically increasing. And, crucially, this support size goes to infinity as Noller goes to infinity.
Okay, let's unpack that notation a bit. That's basically the effective number of unique correct outputs you need to cover the ground truth distribution 5-val with at least probability alpha.
Exactly. Yeah. You're essentially measuring the required diversity of correct answers. If the task is long form, as the problem size grows ground, like going from 5-digit addition to a 1,000-digit addition, the space of possible correct answers just explodes.
Right.
Which means the model needs an output mechanism that's expressive enough to accurately produce this potentially unbounded variety of specific long correct sequences.
The paper gives some good concrete examples too, right? Like multi-digit addition where $' is just the number of digits.
Yeah, or sorting, where null is the number of items. Or even code fixing, where null could be the number of functions you need to change. All of these inherently require increasing memory capacity to solve as null gets bigger.
And this leads directly to you called it devastating conclusion of theorem 2.1, which applies specifically to GSSMs operating in either COT only or these single-turn settings. Can you walk us through the intuition of the proof? Why does having fixed memory inevitably doom length generalization in these cases?
Sure. The theorem basically states that for any long-form task, once you get beyond a certain complexity, any COT only or single-turn GSSM, let's call it dollar, will have an error that's guaranteed to be large. Specifically, 1 alpha.
So high error guaranteed.
High error, yeah.
Right.
And the key is that finite state space, small dollars. Since the GSSM keeps a fixed size state representation of the solver, no matter how long the input is, the total number of unique sequences it can possibly produce at its output layer is strictly bounded by the size of that state space.
So if the model is deterministic, its final output, whether that's a thought sequence or the final answer, it's completely dictated by the final fixed state dollar it reached just before generating that answer.
Precisely. If we think about the model generating some output sequence, the number of possible unique output sequences, let's say $1, is bounded by the size of the state space.
Yeah.
Plenty of dollars.
Okay.
Now, if the task complexity dollar gets large enough, so 1D and end all the required Becher's correct answers, that so powerful dollar term, must become larger than the model's fixed capacity dollars.
Ah, I see. That's a fundamental bottleneck then. The model literally cannot generate the necessary range of correct outputs because its internal memory, or knowledge storage, is physically too small to differentiate between all the possible correct answers that the long-form task demands.
Exactly. It's not about the model being smart enough. It's about not having enough, digital capacity to actually express the required answer space.
It's a hard limit on expressive power imposed directly by that fixed internal memory.
Yeah. And the paper formalizes this by looking at 3 common ways models operate, sort of derived from the ReACT framework.
Okay, the 3 settings.
1, COSI only. The model just uses internal thoughts, no external help. Clearly limited by theorem 2.1.
Right.
2, single-turn tool use. Here, the model issues 1 command, gets 1 observation back, then generates its final output.
Still limited.
Still limited.
Yeah.
Even if that observation is huge, the GSSM still has to somehow compress all that information back into its fixed state civil hours, before it decides on the final output.
Right.
So it's still vulnerable to Theorem 2.1. And 3, interactive tool use. This is where arbitrarily many commands, thoughts, and outputs can be interleaved. This back and forth, this dynamic capability. That's the theoretical escape hatch.
Okay. And this brings us neatly to the key positive result, Theorem 2.2. The idea that this interactive tool use is both necessary and sufficient for GSSMs to finally overcome their memory bottleneck and achieve length generalization, at least on tasks that are computationally tractable.
This is probably the most crucial theoretical finding of the paper. It shows that a GSSM learning algorithm, let's call it $8, when it's trained on these interactive tool use trajectories, pi to aligned, can actually learn to keep its error low, say below epsilon, for arbitrarily large complexity, dit or den $.
So in essence, the GSSM can be taught to just outsource its memory.
Pretty much, yeah. And the mechanism they use to prove this is actually quite elegant. It involves simulating a Turing machine.
A Turing machine, okay.
It completely separates the role of the fixed memory model from the unbounded memory requirement of the task itself.
How does that work?
It's a constructive proof. They define a simple memory tool oracle. Let's call it $. This tool basically provides read-write access to some external memory. Think of it as the Turing machine's infinite tape, using a simple planar that can move left and right.
Okay, so the GSSM's role gets simplified.
Drastically simplified. The GSSM itself, the Mamba or the LSTM, it's no longer responsible for storing, say, the 1,000 digits of the addition problem or all the intermediate results.
Right. It doesn't need infinite internal memory.
No. It only needs to be responsible for tracking the fixed transition function of the underlying algorithm being executed.
So the GSSM uses its internal fixed state $, just to keep track of the current state of the simulated Turing machine, like its control unit state.
Exactly. And it issues commands things like read the symbol of the pointer, write a 5, or move the pointer right to the external memory tool, which manages the tape.
Okay. So the GSSM only needs to learn the actual rules of the algorithm, like the rules for long addition or multiplication, which are fixed and finite.
Precisely. It just needs to learn that fixed, finite set of rules. Let's call it $3.
And if the model is trained on examples up to some complexity, another $, it learns all those state symbol transition rules in $.
Right.
And since the rules for, say, addition don't change whether you're adding 5 digits or 10,000 digits.
Exactly. The model can then just execute that learned algorithm indefinitely using the external tape.
So the internal learning task is fixed and finite, just learn trialer, while the external computation can be unbounded.
That's the core idea. And it also explains why only interactive tool use works. Think about this single-turn GSSM again. It gets one big observation, maybe the entire contents of the external memory at some point.
Yeah.
But it still has to compress all of that back into its fixed state as dollars, which completely defeats the purpose, right? It pushes it right back under the limitation of Theorem 2.1. You need that back and forth interaction.
That theoretical foundation seems really solid.
All right.
Okay, let's see how they took this from, the theoretical realm into actual experiments. They tested Mamba, LSTM, and GRU models, all GSSMs, against transformer baselines like Pythia and a Mistral-style model with that fixed sliding window attention. And they started with those synthetic arithmetic tasks.
Right. The initial experiments were really focused on verifying this Turing machine simulation idea. They used a pointer-based memory tool. Special commands like pointer1.read or pointer2.moveleft were just injected into the sequence.
Okay.
And a crucial detail: the model's thoughts and outputs were automatically appended to the context memory, making them accessible via the pointers. This simulates like a functional scratchpad.
But the commands and observations themselves were discarded.
Yeah, they were discarded from the context history. This ensures they don't just artificially inflate the context length that the GSSM has to process internally. Keeps it efficient.
Makes sense. And the headline result on multi-digit addition? That was pretty spectacular, wasn't it?
It really was. They trained models only on addition problems with up to 5 digits.
Just 5 digits.
Yeah. And Mamba and the LSTM, they learned the classic long addition algorithm so well that they achieved perfect 100% accuracy when tested on 1,000-digit addition problems.
Wow. 5 digits to 1,000 digits perfectly.
Perfect generalization. This is basically the empirical proof of Theorem 2.2 right there in action. They didn't just maintain high accuracy, they showed absolute length generalization, solving a problem vastly larger than anything their internal state space could possibly hold on its own.
And the transformer baselines.
Predictably, they failed to extrapolate much. Their accuracy just plummeted really quickly once the test case size got bigger than what they saw in training.
They also extended this to multi-digit multiplication, right? Which is structurally similar, but algorithmically a bit more complex.
Yeah, they trained on multiplying up to 10 digits by just 1 or 2 digits. And again, Mamba and the recurrent models kept really high accuracy all the way up to 1,000-digit multiplication. It shows that the learned transition function trait dollars can be quite robust, even for more complex iterative algorithms.
And the ablations they ran seem crucial here, too, providing the counter evidence.
Absolutely, that's in Appendix D.7. They explicitly trained models using only straight-T or only single-turn tool use. And even when these ablated models got perfect accuracy within the training distribution,
Yeah.
they showed basically little to no length generalization when no dollars was increased, which empirically confirms that interactive memory access isn't just helpful, it's actually necessary for this kind of extrapolation.
They also tried mixing tasks, right? Like seeing if learning addition helped with multiplication.
Yeah, that was in Appendix D.8. What they found was kind of interesting. Code training addition with multiplication only gave some marginal temporary boosts if they used extremely limited training budgets like only 250 or 500 steps. But once the models got enough training, maybe around 800 steps, that benefit just disappeared. It suggests the length generalization really depends purely on the model fully learning the transition function $3 for the specific target task, not so much on leveraging structural similarities between tasks.
Got it. Okay, let's shift gears to the logical graph task. This tested algorithmic reasoning, not just arithmetic. It involved solving a directed acyclic computation graph, a DAGI of Boolean operations represented as Python code. That sounds much more abstract.
It is, and for this, the memory tool was different too. They moved away from that linear pointer access to more of a search-based mechanism. The model used a command like find x.
Like a grep command.
Exactly, like grep. It searches the entire context, which includes all the previous thoughts and intermediate results the model generated for its specific patterns and material.
So the idea here is memory augmentation through retrieval. The GSSM has to use its internal state to figure out which intermediate results it needs, issue the right find command, and then use whatever comes back in the observation to continue its computation path.
Precisely. And the results. Strikingly consistent with the arithmetic tasks. Mamba and the recurrent models, they successfully extrapolated from training on graphs with only one other bilawar nodes, all the way up to 1,000 dollar nodes.
1,000 nodes?
Yeah, maintaining near-perfect accuracy, like 98 to 100%. Meanwhile, the transformer baselines really struggled again. That Mistral-style model, its accuracy dropped from 100% down to just 9% by the time they reached N500 nodes.
Wow. So that really validates the idea that interactive search tools can also overcome the GSS memory bottleneck, even for complex logical reasoning.
Seems so, yeah.
Okay, before we jump into the big coding task, we should probably mention the limits they observed with the Tower of Hanoi problem. That one's known for having an exponential solution length, right? Like 2 nully-1 moves.
Yeah, the Tower of Hanoi is almost like an adversarial task for sequence generation. The sheer length of the correct output sequence is enormous.
Yeah.
The difficulty isn't just the algorithm itself, but generating that exponentially long, perfect trajectory.
So what happened there?
Well, they saw much more modest generalization. Mamba went from 8 disks in training up to 12 disks, but only with about 49% accuracy. And they noted that even if the token level accuracy was super high, like over 99.75%,
Yeah.
the cumulative probability of generating a completely correct sequence that's hundreds of thousands of tokens long just gets vanishingly small. It approaches zero.
Right, tiny errors accumulate.
Exactly.
Yeah.
So this shows that the tool use augmentation, it solves the fixed memory problem, but it doesn't magically solve the separate problem of generating incredibly long, high-fidelity sequences perfectly.
Okay, that's an important distinction. So now let's move to the most realistic setting, the code-fixing task. This feels highly relevant for anyone building agents today. This is where the theory really meets practice.
Yeah, the setup here was critical. They generated these synthetic code bases. Each had not Python functions forming a dependency graph. And the bug was designed to be tricky. It required the model to trace the flow of a variable, v10, and pass it through that entire dependency path, maybe from main.p all the way down to some function called foo.pi.
So it inherently requires looking at multiple files and understanding how they connect.
Exactly. And they trained the models on code bases, up to 116 6me functions, using a pretty hefty 8,192 token context length. That size alone challenges many architectures.
And crucially, they didn't just generate one type of training data, they collected trajectories from 3 different kinds of agents.
Right. Agent 1 was the single-turn agent. This one tried to do everything at once, print all the relevant files, make all the changes, and then output the completely fixed code in one go.
Which mirrors those COT-only or single-turn theoretical settings that are limited.
Exactly. It's designed to fail in complex cases due to context limits or just the sheer complexity of doing it all at once. Then you had Agent 2, the interactive agent. This one worked iteratively. It would run the code, see the error, fix maybe just a few files like the create again, and repeat that loop until the bug was gone.
Okay, that sounds more realistic.
And Agent 3 was the distillation agent. This was basically an emulation of a powerful existing model, SWE agent LM32B, which was specifically prompted to debug interactively using bash commands. So Agents 2 and 3 both represent that ideal interactive trajectory the GSSM should learn.
Got it. So they fine-tuned Mamba 1.4b and Pythia 1.4b on these different trajectory types. What happened when they tested them on code bases larger than the training data with un-$16.6 functions, the extrapolation phase?
Okay, so in distribution, less than $60, the transformer, Pythia, actually did slightly better than Mamba, especially on the data from the distillation agent.
Okay.
But out of distribution, the results were, well, exactly what the theory predicted. Mamba maintained significantly better accuracy as the code base complexity increased, but only when it was trained on the interactive trajectories from Agents 2 and 3.
So Mamba successfully learned the iterative debugging process, the sort of transition function for that algorithm, and it could generalize that fixed process to much larger code bases by using the tool, presumably bash commands, to query the external file system as needed.
Precisely. And here's the perfect empirical nail in the coffin for Theorem 2.1. Mamba failed, and failed badly, on the larger, complex code bases when it was trained only on the single-turn Agent 1 trajectories.
Because those trajectories didn't provide the iterative loop needed to simulate that unbounded memory access?
Exactly. Mamba just hit the wall imposed by its fixed internal state, just like the theory said it would. It's a really clear validation of the necessity of interaction for these GSSMs on complex, long-form tasks.
That real-world demonstration is powerful. It definitely moves the conversation beyond just abstract arithmetic into something like practical software engineering. Okay, let's try and synthesize all these findings and think about the broader implications the authors are pointing towards. We started with that efficiency versus accuracy trade-off. It really seems like interactive tool use lets you have your cake and eat it too. You get the SSM efficiency without the inherent accuracy limit.
Yeah, it effectively collapses that dilemma. The GSSM's structural limitation, its fixed memory, is only really a limitation if the task forces all the necessary information to be crammed inside the model itself.
Right.
By introducing this unbounded external memory, accessed via interactive tools, you transform the GSSM. It goes from being just a bounded compression engine into being a highly efficient control unit for a larger computational system.
This also seems to suggest that SSMs might be a uniquely natural fit for agentic systems, maybe even more so than transformers, despite the transformers' larger internal capacity. Why would that be?
Well, there may be two main architectural reasons. First, just efficiency in parsing inputs. Agents lean heavily on tools, right? And tools often spit out huge amounts of messy content, think thousands of lines of code, long log files, massive search results pages.
Yeah, tons of text.
SSMs, with their linear scaling, are perfectly suited to rapidly process and sort of compress this massive, maybe non-critical input content without spending those ultra-dollar compute cycles on every piece of it.
That makes sense. And the second reason?
The multi-turn interaction itself.
Oh. Right.
Which is absolutely necessary for complex tasks like that code fixing example. These interactions quickly cause context window overflow issues for standard transformers. Every command, every observation, every thought, every previous output, it all has to get stuffed into the KV cache, constantly driving up that compute cost. The GSSM's efficiency really helps mitigate that severe context management problem you hit in iterative agent work. They can process the interaction history efficiently, keeping only the necessary state in their fixed internal memory and effectively leaving the full history to the external tool or memory.
So this really shifts the fundamental way we should evaluate these models, doesn't it? We can't just look at LLM architectures as standalone text generators defined only by their internal capacity anymore. This paper seems to force us to analyze their performance as part of a system.
I think that's the most profound implication here. Architectures that we might have previously considered weaker or less capable when run in isolation, maybe because they lack that unbounded global attention, could, paradoxically, perform better when they're properly integrated into a well-designed agentic system.
So the system design, especially that interaction protocol, becomes potentially more important for long context performance than just the model's raw architectural class.
Yeah, it becomes a determining factor.
That's a pretty fundamental challenge to the sort of prevailing wisdom that only massive, globally attending models can handle truly complex long-form reasoning. Okay, so to quickly synthesize what we've covered in this deep dive, the paper formally established that interactive tool use is theoretically necessary for these fixed memory GSSMs to achieve length generalization. Code-only and single-turn models are mathematically bounded.
And we saw this verified empirically across really different domains. Mamba, when trained on those interactive trajectories, achieved perfect generalization on 1,000-digit arithmetic. That near-perfect extrapolation on 1,000-node logical graphs, and kept superior accuracy on complex code-fixing tasks way outside its training distribution. That ability to effectively simulate unbounded external memory transforms the efficient SSM into an unbounded computational engine.
So it suggests that the next big leap in scalable, long-context AI might not necessarily come from finally breaking that quadratic complexity barrier with a brand new core attention mechanism,
Right.
but maybe from mastering the design of the external system the model interacts with. The efficiency challenge is still there, but maybe the solution lies more in the interaction protocol, not just the fixed architectural constraints of the model itself.
Exactly. I mean, the paper basically proved that for these models with fixed internal memory, the ability to solve really complex long-form tasks isn't fundamentally about the internal architecture size, it's about the interaction protocol.
Yep.
And that forces us to ask, a critical question. Is the next huge breakthrough in long context AI going to come from a fundamentally new core model architecture? Or is it going to come from a breakthrough in how efficiently we manage the model's interaction with its external environment, its tools, its memory? The future of LLMs as effective agents might hinge entirely on optimizing the efficiency of that external tape, not just tweaking the internal control unit.
A really compelling argument for system architects and anyone building agents out there. Thank you for joining us for the deep dive.